So shall I start off?
So it's my pleasure to introduce Sheng Meng from the Korea Institute of Advanced Study, who's going to speak on the automorphism group and its Jordan property.
Okay, thank you very much for the introduction. Okay, today I'm going to talk about the automorphism group of varieties and the Jordan property. So the talk mainly consists of 4 parts. The first, I will talk about some the definition and some basic properties. And then I will discuss sketch the proof for the case for the projective and the Kähler varieties. And then third, I will mention a key step in our recent progress dealing with the finite subgroups of the automorphism group of X fixing some very good locus. And then I will talk about our proof for the Jordan property for automorphism group of Fujiki's class. Okay. So let's start. So let's first recall the definition. Given simply a group G, then we say G is Jordan if it has almost abelian finite subgroups. So precisely, it means that there is a Jordan constant J such that every finite subgroup H containing G has an abelian subgroup H1. H1 is the subgroup of H, and the index is bounded by this J. And this constant J depends only on the group G. Okay, it is probably named after Camille Jordan, who in 1878 proved that the general linear group has a Jordan property. But we need to work over a field K of characteristic 0. And the simple exercise is that you can see that if you work over characteristics P greater than 0, then the general linear group is not Jordan, because you can consider this kind of finite subgroups of SL and FPR. You can easily check that they're just the Jordan constant will go to infinity. Okay. So, and before we talk about our question, I will mention the very fundamental group exercises which will be frequently used later, and they're simple. So given a group G, of course, we want to decompose it into in an exact sequence 1 G1 to G to G2 to 1, and we want to see whether either 2 of them can imply the third. But in general, it is not true. But first, there are several properties here. So if G itself is Jordan, we see the subgroups. The subgroup is always Jordan. And secondly, if G2 is a quotient, has bounded finite subgroups, meaning that there is a constant C such that all its finite subgroups of G2 has order less than this constant. So we call G2 has bounded finite subgroups. And if so, and together with G1 being Jordan, then we can imply G has Jordan property. And thirdly, if G1 is a finite group and G is Jordan, then the quotient is always Jordan. Okay, this we will not use this property today, but this is also very important here. First, if G1 has no non-trivial finite subgroups, no non-trivial finite subgroup, meaning that something like a G1 in the Ashback group theory, it is like the unipotent group, and the G2 has Jordan property. We can see that we can show the middle one is a Jordan group. As I mentioned, that the exact sequence cannot preserve the Jordan property, but if it is it splits, meaning if G is the direct sum of G1 and G2, and the G1, G2 are Jordan, then we can see the middle one, G, is Jordan. The final one is very important. So if G1 has bounded finite subgroups, and G2 is Jordan, here we see it is different with 4, because the 4 requiring there is no non-trivial finite subgroup here. But here we only require G1 has bounded finite subgroups. So this assumption is weaker. And G2 is Jordan, of course, here we need it. And we assume that it's finite abelian subgroups can be generated by at most n elements. Then we can see that G is Jordan. Okay, so we will use 6 frequently later. So this proposition. Okay. Any question? Okay, if no, I'll move to our main part. Okay. So now we come to our question. Here is an example. So you can try to construct the exact sequence of groups such that G1, G2 are Jordan, but the middle one is not Jordan. The example will be given later. Okay. And there is also a very famous theorem which I need to mention is the Minkowski's theorem, which says that if the field is Q or number field, then the general linear group has bounded finite subgroups. Okay. Okay. So now let's come to our question, which is asked by Popov. So he asked, today we will mainly study these two questions. So is the biholomorphic or the automorphism groups auto X Jordan or not for an algebraic manifold, algebra variety? A second is for a compact complex manifold or singular case, a compact space. This question in general cannot be generalized further because Popov said that there are non-Jordan automorphism groups of connected non-compact complex threefolds. So this assumption here cannot be weakened. And Stickles and Seiber and Zappel, they say that there are non-Jordan diffeomorphism groups of compact real manifolds. So we need here a complex manifold here. And we also need to consider the automorphism group here. So we need here it to be automorphism group instead of the birational automorphism group, because Popov and Zahin show that for algebra surfaces, the birational automorphism of the surface S is Jordan if and only if S is not birational to the product of P1 and the elliptic, here E is an elliptic curve. So here it gives an example which shows that the extension cannot preserve the Jordan property. So we have the very natural exact sequence here, the birational automorphism P1 cross E, and it descends naturally to the automorphism group of the elliptic curve E via the Abernathy map. And the kernel can be viewed as a automorphism group of the P1 over the function field of E. And it is clear to see that this group is a general linear group, and this group is an extension of simply a finite group and E itself. So this is automatically Jordan. So this one is Jordan, and this one is Jordan, but the middle one is not Jordan. Okay. So these three questions say that many of our assumptions cannot be generalized. So here it is a automorphism here and and compact here, complex here. Okay. I'll mention some other results which we will not use today. First, Montes showed that if we consider diffeomorphism automorphism group of a real compact manifold, if this Euler number is not 0, then he showed that the diffeomorphism automorphism group is Jordan. And Bandman and Zahin proved that the automorphism group of not necessarily projective or compact algebra surfaces, the automorphism group is Jordan. So I just mentioned birational S may not be Jordan if S is birational to P1 cross E. But for automorphism group, it is okay. And Prokhorov and Sheremov proved the Jordan property for the automorphism group of compact complex surfaces and the Morrison threefolds, which means it is a compact complex space bimeromorphic to some projective threefold. Okay. So for these two cases, one is for compact surfaces, and another one is for Morrison threefolds. Here I need it to be compact. Okay. In positive characteristics, as I said, the general linear group, even the general linear group may not be Jordan, but if you consider a weaker assumption called so-called P-Jordan property, I will not talk this in deeper here. So roughly, it means that we consider the finite subgroup irrelevant with the P power part. So Fei Hu proved that the automorphism group of a projective variety in positive characteristics, although it may not be Jordan, but it has the so-called P-Jordan property. And it is a coincidence that today in arXiv we noticed that there is a new preprint by Yifei Chen and Sheremov. They show that in positive characteristics, the birational automorphism group of a surface, S here, S is a surface, sorry. Birational automorphism group of a surface has a P-Jordan property if and only if S is not birational to the P1 cross D. This is something like the characteristic 0 case. And they prove that in higher dimension, if the Kodaira dimension is non-negative and the X is smooth projective, then automorphism group has a Jordan. Here it is the Jordan property, not only P-Jordan. And it will be talked by Chen in tomorrow's seminar of AGEA. Okay. Okay, now I'll mention some very important results today, which will be mainly used. Okay, so there are two, now we focus on characteristic 0 or compact complex manifolds. So the following two results is our initial point today. So auto X is Jordan for projective manifold or projective variety, which is proved by me and Deqi Zhang. And later it is generalized by King that it holds true for compact Kähler manifold or compact Kähler variety. Okay, the proof here is important. I'll sketch it. Okay, so first we can consider the pullback action on the singular cohomology with Q coefficient H2x cubed, and clearly its action, its representation is contained in the general linear group of this finite dimensional vector space. And by Minkowski's theorem, we know this group has bounded finite subgroups. So we consider the exact sequence, the automorphism group, and its action on the singular cohomology, and denote by the kernel, the auto tau X. And since this one has bounded finite subgroups, if you check the previous, in the second page of this slide, to show the Jordan property of auto X, it suffices for us to show the Jordan property of this kernel, the auto tau X. Okay. Then we denote by the auto 0x be the connected component containing the identity element of the larger group. And clearly, auto 0x is a subgroup of auto tau X. This is because the action here, because this space is this group is a discrete group, and auto 0 is a connected group. So the action is trivial. So we see automatically auto 0 action on the H2XQ is true. So auto 0 is containing the kernel here. Therefore, furthermore, we can fix the Kähler class omega in the H11 because we assume our X is either a projective manifold or a Kähler manifold. So such class always exists. And we denote by auto omega here by the automorphism which preserves this class. And one can easily see that this is the group which contains the auto tau X, because auto tau X needs to fix every class of H11 by the Hodge decomposition, because we can embed H11 into H2XR. And since this group action on H2XQ is trivial, so the action on H2XR and has on the H11 class, every H11 class is trivial. Then by a result of Lieberman and Fujiki, we see that the index of auto omega and auto 0x is finite. So together we can see that auto x quotient by auto tau, auto x quotient by auto tau has bounded finite subgroup, and the auto tau quotient by auto 0 is finite. So together auto x quotient by auto 0 x, so which I call it the component group, has bounded finite subgroups. So once more, we see that to show auto x is a Jordan group, we only need to show that the kinetic component auto 0x is a Jordan group. Here I highlight that we need x to be Kähler. Okay, sorry that I forgot to mention two basic facts. First, we need to use the Grosontics result that if x is projective, then the auto 0x here is a connected algebraic group. And in the complex geometry setting, by duality, that if x is a compact complex manifold, then the auto 0x is a connected complex Lie group. Okay. Now here there are two different methods to show that the kinetic component auto 0x is a Jordan group. Our trick is to use the theory for algebra group theory. First, we use the Rosenlik decomposition. Roughly, it means that G can be written as the product of G affine and anti-affine part. Here, affine part means the linear part of the algebra group, and anti-affine part is the minimal normal algebra subgroup of G, which quotient being linear. Okay. Anyway, to show that G has almost a bound, and then we show that G has almost a bounded commutator groups of finite subgroups. Then we say that every finite subgroup H has a finite subgroup H1 with bounded index, such the commutator group has bounded order. Okay. Alternatively, Popov recently gave a more simplified proof. Okay. So he proved indeed that every real connected finite dimensional Lie group is a Jordan group. The proof is quite simple. So first, he applied the Katan-Iwasawa-Markov theorem to show that every maximal compact subgroups of G are conjugate to each other. So it means that we know that we consider the finite subgroups of G. And every finite subgroup is a compact subgroup. So it is containing some maximal compact subgroup. And since all the maximal compact subgroups are conjugate to each other, so we can always embed every finite subgroup G into one common maximal compact subgroup. And then we only need to show this one maximal compact subgroup has a Jordan property. So which is obtained by the following fact that compact Lie group always admits a finite dimensional representation. So this means that we can always embed the finite subgroups of G into some common general linear group. So over R over the real numbers. So it has a Jordan property. Okay, so this is roughly the idea of the proving the Jordan property for the projective varieties or scalar varieties. Okay, any question? No, then I'll move.
So here you don't need a uniform dimension of this representation, right? You don't need that one.
Because I already choose the maximal compact subgroup. So I only need to show the Jordan property for one maximal compact subgroup, which is enough.
Okay, thank you.
Okay. There is another very nice trick dealing with the Jordan property, which is quite related to from the geometry point of view, which is called almost a fixed point, which is first dealt by the Prokhorov and Sheromov, and later by a famous result of Birka. So they together show that the birational automorphism group of any rationally connected variety has a Jordan property, and the birational automorphism of and more generally, the birational automorphism group of any projective variety with irregularity 0 has a Jordan property. So in particular, the Kremenov group, which can be viewed as a Galois group of the k, x1, xn n variables over k, has a Jordan property. But here we also need the k equals to 0. The key idea is that 2 can be reduced to prove 1, and then we show that any finite subgroup of G has an almost fixed point on some smooth model. This is by taking G equivalent resolution and G equivalent compactification. And we can show that on such model, G has an almost fixed point, meaning that there is some subgroup H with index bounded by a constant determined only by the dimension n here, such that H has a fixed point on this good model. And moreover, they can choose such model. They reduce the problem to show the case where the model X is simply a final variety with only terminal singularities. Then, by a famous result of Birka of proving the BAB conjecture which says the boundedness of the final varieties of terminal with epsilon KRT singularities. So actually, the automorphism the group H can be embedded into some common general linear group. So actually, the Jordan property of birational X is coming from the almost fixed point property here. And we, for our purpose, we only need this very simple argument here. So if H is a group fixed sum X, then we consider the tangent homomorphism, which sends H to the small h to the tangent map. And such group, this is the group homomorphism, and one can show that this is injective. This result is actually true when H is a reductive group, not necessarily connected. Okay, we will use this lemma later. Okay, so so the following part is about some relation between almost fixed point and Jordan property, which I will skip. Right. So it says that the almost fixed point implies the Jordan property, as I mentioned just now, and the converse in general does not hold. For example, simply consider the abelian varieties and their translations. But however, if you assume Q equals to 0, then the converse holds true. by considering the maximal rational kinetic vibration here. Okay, so I'll skip this part. This is not my main purpose here. Okay, now I'll talk about our main technique today. So we try to, as we noticed that the Camille-Jordan proves the Jordan property because the general linear group has some very good linear property. So, but for our automorphism group of a general variety, it is not necessarily linear. So our first step is to make it as linear as possible. So set up, let X be a connected complex manifold, and let Z containing X be a connected complex submanifold. And we denote by auto XZ the subgroup of auto X which preserves this submanifold. And then we record our previous lemma. If Z is a point, then we have that auto XX has an embedding into the GL of the tangent space at X, which we know this group is Jordan, and clearly this group is Jordan. And then we let E to be a complex vector bundle over Z, and denote by this new group auto E to Z, a subgroup of we denote this symbol by the subgroup of automorphism group of this manifold, which preserves the fiber, which means G sets fiber, G sets fiber EZ to some other fiber EHZ. Moreover, this map is linear. Okay, so there are three ingredients. So first, the G has to descend to the base, descends to an automorphism of Z to Z equivalently. Secondly, it maps the fiber to fiber. Thirdly, it maps the fiber to fiber linearly. Okay. So we have the two notation, auto XZ and auto E to Z here. Then we consider a very fundamental exact sequence. So we consider here this symbol means a tangent bundle. The tangent bundle of X restricted on Z. This is the middle term, and the tangent bundle of Z. And by taking quotient, we get the normal bundle of Z in X. And moreover, we consider for each automorphism of X, we consider the middle term is the tangent map. Since the tangent map G, and as we assume that G preserves Z, then we have the restriction TG restricted on Z, and we can also consider the action of the tangent map by of the restriction of G on Z first, and then take the tangent map. So this is the first to take the tangent map and then restrict the tangent map to Z, and this is the induced. We call it the normal map, and then in particular, we have a group homomorphism N here, which sends every automorphism G preserving Z to NG here, which lies in this group. Okay. A simple lemma is that this is a group homomorphism, and its kernel has no non-trivial finite subgroups. So this is simple because we let G be an element in this kernel with finite order. And since, and by the definition, we see that G lies in the kernel means that NG is trivial. So NG is identity, and NG is identity meaning that the G descends to identity over the base. And moreover, the tangent map G, the tangent map of the restriction of G on Z is identity. So this one is identity map, this one is identity map. So we see this one is a linear map. It can be viewed a linear map, but it is the upper triangular with every diagonal entry being 1. However, G has finite order, so the middle one also has the middle one. This map is also has finite order. So together with it is together with that this is a unipotent action over each point of Z. We noted that this action has to be identity for each point Z belongs to Z. So this together with X being connected, this is important. We show that G itself has to be identity. So we see that the kernel of N has no non-trivial finite subgroups. Okay, any question? Okay, we move on. Okay, in this way, we can do the we further do the equivariant compactification. Because as I mentioned, that early known results mainly focus on the automorphism group of projective variety or compact Kähler manifolds. Few were known about the not necessarily projective or not necessarily compact algebra variety or simply complex manifold. So to study auto E, it is very difficult. So we need to study its compactification. And we denote E by the normal bundle here, and O a trivial line bundle. And let T be the torus acting on this normal bundle, and O by the natural scalar multiplications. So there is a natural T equivalent monomorphism, so which sends every G to this one. In E, it keeps G, but on the second term, it is simply the identity map. And then we have the following auto E to Z equivalent commutative diagram. Okay, this is very natural. And we denote by PE direct sum with O, simply the quotient of this new vector bundle by the scalar action. So this is now an analytic PR bundle over Z. Okay, now we consider the homomorphism. So now we have the compactification by E to the projective bundle of E sum with O, and we have the group homomorphism of this of this group to this group by the natural T quotient, and we know by composite with this group homomorphism, and together with with this group homomorphism, we show that this is still a monomorphism. So this is still injective. Together, we see that there is a natural equivariant compactification from E to PE direct sum with O. Okay, so now we have the following result. So let X be a connected complex manifold and Z a connected complex submanifold. Then the automorphism group of X preserving Z is a Jordan group if the automorphism group of the compactification here of the normal bundle is a Jordan group. And suppose Z has some good locus. For example, if Z is further compact Kähler, then we see that auto XZ is Jordan. This is because this PR bundle of a compact Kähler manifold is still a compact Kähler manifold. And that, as we know, the automorphism group of compact Kähler manifold is a Jordan group. So we see this group is a Jordan group. Okay. Okay, any question? If no, I'll move to the case for the Fujiki's class. Okay. Okay. Recall that the definition of Fujiki's class C, which is a compact complex spaces, which are meromorphic image of scalar manifolds, or equivalently, a definition is that it is a compact complex spaces which admits a big one-one form. And the following is our main result together with the Fabio Perroni and Deqi Zhang. So we eventually show that the automorphism group of a complex space lying the Fujiki's class has the Jordan property. Okay. So before that, we need some preparation work. So we can first take a resolution which is auto X equivalent. So in this way, we may first assume our complex space is smooth. So it is a complex manifold. So this is the first step. Secondly, a compact manifold has only finite many kinetic components. So we may pick the largest component, and we may assume X is connected. This is not our preparation work, but worth mentioning now. So by Cho's lemma, there is a projective biholomorphic map from a compact scalar manifold to our X here. However, we cannot show the equivalency here. If we can show the equivalency, then our result here is very simple. So this leads to a very natural question. So let X be a complex manifold in the Fujiki's class. Can we find an equivalent biholomorphic map X tilde to X such that X tilde is compact scalar? Later, I'll mention a little bit the difficulty here. Okay, so in general, this is very, I don't know if this is true or not, but at least this is very complicated. There's another approach. As I just mentioned that we already know that the Jordan property of auto 0x because this is a Lie group. So if we can show that the component group have bounded defined subgroups, then auto X is automatically Jordan. However, this part is also very complicated. Weakly, we only need to show that the auto tau X quotient by auto 0 is finite or has bounded finite subgroup. Recall that auto tau is the subgroup which acting trivially on the H2XQ. Okay, so these are two natural questions which might be irrelevant with the Jordan property and have their own interests here. Okay. Okay. Now I will state our simple trick avoiding this the previous two questions. Okay. So now we fix our X to be smooth, connected, compact in Fujiki's class, and then we fix the Hermitian form omega. And by definition, there is a big 1-1 class in the partial bar 1-1 cohomology, which means that the following equality holds weakly in the sense of currents. Here, epsilon is some small real number greater than 0, and phi is the quasi-Plurissa harmonic function phi. And the T is, we call T here is the scalar current contained in this big class. And we define the non-scalar locus, which is similar to the augmented base locus in the setting of projective varieties for big divisors. But here we denote it by E of alpha, to be the intersection of the singular locus of T, where T is taken to be all the scalar current in the big class alpha. And here, singular locus of T is defined by the singular locus of phi, which is the union of points of x of points x such that phi is not smooth at x. And by a theorem of Bergson, we can pick some good scalar current T in the class, such that the non-scalar locus is just the singular locus of this one single scalar current. Okay, and furthermore, we can apply Demay's fundamental regularization theorem for currents, which says that by definition, the singular locus of T is singular locus of phi, and phi is the quasi-pitch function, and such function can be written locally as in this form, where C here is a constant, and H is a smooth real function, and Fi are holomorphic functions. And we denote by the ideal shift, the I here be the ideal shift generated by the holomorphic functions Fi. Then the non-scalar locus is simply the reduced part of this ideal, the zeroth of the ideal shift. So it is simply the 0 points of F1 till Fn. And this together, this globally forms a closed analytic subvariety of our X here. Okay, I'll come back to the first question. Why this question is difficult? Because in general, to get the scalar model of our Fujiki class X, we need to do, our first step is to blow up the ideal shift instead of blow up the reduced locus or the non-scalar locus over here. First of all, we cannot show this non-scalar locus is auto X equivalent. And even if it is auto X equivalent, we cannot show the ideal shift, which has some multiplicities. We cannot show the blob is auto X equivalent. So this causes a very big gap here. Okay. But anyway, for us, this non-scalar locus is good enough. Okay. First, I have to give a remark that if the non-scalar locus is empty, this means that the scalar current is already a smooth, and hence, so it means that it is a scalar form, and hence X is already a scalar manifold, and everything is done then. And there are several basic effects that closed analytic subvarieties and the meromorphic images of X are always in the Fujiki's class C. So our non-scalar locus is still a Fujiki's class, and the partial bar lemma holds for the Fujiki's class, which implies that we can freely use the equivalent, Bott-Chen cohomology and the Dolbeault cohomology or Dirac cohomologies. And moreover, the Hodge decomposition holds true here. In particular, we can use the embedding of the H11 to H2X of R. As I mentioned, we need to show the auto-tau. We only need to show the Jordan property of auto-tau, and auto-tau has something very close. Auto-tau is defined over H2XQ, and the equivalent to the action on H2XR. So we need the injection here. Okay. Although we can not, as I just mentioned, that we cannot show that the ENK alpha is auto-equivalent, but we can show that the non-scalar locus of alpha is auto-tau invariant. The reason is simple. You consider any G in auto-tau, the action on H2XR is identity. First, the action on H2XQ is identity. So this one is trivial. And then by this injection, we see the action on the 1-1 class, all the 1-1 class are identity. So it preserves, in particular, this big class alpha. And since the non-scalar locus is independent of choice of this alpha, so we see the non-scalar locus is invariant under G. So in particular, it is invariant under the action of order tau X. Okay, now we can try to finish our proof. Okay, so our setting is that we need to show the Jordan property of order X. So we only need to show the Jordan property for order tau X, and I give a notation G here. And we fix a big 1-1 class alpha here, and we denoted the non-killer locus E by Z here. Now we try to do several finally many steps replacements. Okay. So first, if Z is although our X is smooth compact, Z may not be smooth and may not be scalar or may not be connected or may not be. It is compact also. So if Z is already a compact, smooth connected scalar, then we stop. Okay, we don't need to do anything here in this step. So we consider the other case. So if Z is not connected, then we replace G by a finite index subgroup, preserving all connected components of Z, and then we replace Z by one connected component. Okay, so in this step, we replace Z by some connected one. If Z is not smooth, then we replace Z by the singular locus of Z, because because Z is G invariant, and also the singular locus of Z is also G invariant. Of course, if you do so, the singular locus of Z, if even Z is connected, the singular locus of Z may not be connected. Okay, so we may need to do step 2 and step 3 several times. And if Z is not connected, if Z is smooth connected after finally many steps of 2 and 3, but it is not scalar, then we can pick some big 1-1 class beta, which is this is a 1-1 class in Z, okay, H11 of Z, and replace Z by the non-killer locus of beta, and G by the following subgroup G2, which is the subgroup which acting trivially on the H2ZQ. And we can always do so until we meet step 1, because Z is compact. So each time you reduce the number of kinetic components or you reduce the dimension, so you can only do finite many replacements. So eventually we end up with step 1, and we only need to show that the new group G is a Jordan group. And it is because now our G is a subgroup of automorphism group X, preserving Z, where Z is in step 1 is a connected, compact, smooth scalar manifold. And as we see that this group is a Jordan group, so we see the Jordan property of G and the Jordan property of auto X. Cool. So this finished my proof. I think I'll stop here. Thank you very much for listening. Okay. Thank you.
Thank you. Okay, we have some time for some questions.
Of course.
I saw you put, I didn't know one could do this. You put the slides in the chat, is that right?
Huh? Put what?
The slides on the chat.
Yeah. In case I'm in a hurry, so you so you
No
can
worry, no,
see.
it's great actually. Yeah, I didn't know it was possible. Yeah. Okay. Do we have any questions from anybody? If you're shy, you can write them in the chat. I'm happy to ask on your behalf.
You need to say that G tau has a finite index in G.
Yeah, yeah, of course. Yeah, this is because this group. This is because this is a finite dimensional representation. Yeah, So it has bounded finite subgroups. So G tau may not have G over G tau may not have finite index. It only has bounded finite component group because this group is large. Because the representation of G on H2ZQ is very large. It's the GLNQ. It only has bounded finite subgroups. So this index here is not bounded. It has only bounded finite subgroups.
Yes, thanks. Yeah.
Okay. Are there any more questions?
I have a question in this step, those steps. So I think there is a case, for example, the dimension of z is 0. So you reduce z to a point, and then I think it's fine because you don't have.
If z is a point, then it is automatically killer. It is also complicated, but indeed it is very simple because we have this result. We have this result. Auto xz is a subgroup of GR of the tangent space at z. This is the isomorphic to this one. This one is short. Okay.
Okay. Thank you.
Okay. Thanks. Are there any more questions, comments? No? Okay, well, in that case, let's thank Sheng. Thank you.
Okay, thank you very much. Okay.